Hi, we're going to talk today about what dynamic device key generation, also known as DDKG, is, what it does at the heart of the Keyscaler platform, and how it enables devices to be the key to authentication at IoT scale. So, IoT devices are awesome, but for them to be IoT devices, they need to be internet connected, otherwise they're just devices. They need to identify themselves in a secure way to the server. Historically, this was done using hard-coded or manually set usernames and passwords. Certificates are a much better solution than username and passwords. They help to establish trust in a much more secure manner, as well as allowing industry standard encryption to be used. They can be revoked and managed, hold information about their chain of trust. If we put a unique certificate on an IoT device, then it'd be able to identify itself, set up secure communication without needing a username and a password. The problem with IoT, however, is the scale. There are millions of devices, and they end up spread all over the world, in remote and hard-to-access locations, strapped to cows, up mountains, towers, deep inside factories and oil pumps, and moving around the world in cars, planes and trains. To put these certificates on devices quickly becomes a massive task, so automation here wins. And what if there was a way to have a device do much of the work itself? And that's where Keyscaler's DDKG comes in. So we'll have a look about how a device authorizes itself with a server without needing to hard-code any credentials. We're going to make the device the key. So we're going to walk through a DDKG authentication request from a device to a server. And the start point is a device contacting Keyscaler, requesting authorization. This kicks off the authentication process, and Keyscaler gets itself ready for the handshake. First, the server generates a challenge, just a random chunk of data. It sends that challenge over to the device and starts to listen for the answer to its challenge. These challenges are time and device bound, and so only the real device can sign the challenge, and it's got a limited time window to do it in. On receiving the challenge, the device starts its DDKG process to generate a key. Using that derived key, the device can sign the challenge and send it back. Nothing sensitive sent over the internet here, it's just that random data that's been signed. The integrity of that signature is then tested by the server, by Keyscaler, and validated to be from the correct device. Final handshake, and we close out the authorization. And this is the point that the server can push down and let the device know any news, any certificates that it needs, some software updates, all that type of stuff. So, wait a second then, there was a bit of a gap in that explanation. How did that device just generate its own key? And the answer is, it derived it from its own attributes. The device is able to derive the key based on information it knows about itself and the environment it's in a manner that continually establishes the integrity of the device. So devices are made up of lots of components. Sometimes there might be multiple components of the same type, which we call instances. And within each instance of a component, there are loads of different attributes. Now this makes a little bit more sense if we look at an example. Here's a hard drive. So a hard drive is a type of a component. This device has two hard drives, so there are two instances, and each of those hard drives has loads of information available. Things like its serial number, how it's connected, information about its behavior. By itself, a single hard drive isn't enough information to uniquely identify a device. In reality, we check loads of components, everything that the device can identify. Network information, all the hardware components, and even in some situations environmental information, such as its GPS location. We've also got some synthetic device material that's generated by the device, and this helps to prevent cloning attacks and spoofing attacks, as well as helping to protect the DDKG challenge itself. It helps to increase the DDK attribute entropy and includes some hashing, device attribute salts, and nonce and some other bits and pieces. But with all those attributes combined together, a device is able to form a key, and it follows a recipe called SSS. A SSS is the attribute selection, attribute sequencing, and byte sampling. And here's what that looks like step by step. In stage 1, attribute selection, we get a randomized selection of attributes that are used for DDKG. Notice in here that synthetic key, just a value in there that's burned and changed with every successful authentication. We've got a wide spread of different information from different components, attributes, and we can see the values in there. In stage 2, attribute sequencing. This refers to the order and the number of repetitions for the selected attributes, and we form a block of data. In reality, these are salted with the synthetic key, and so you can't actually read them in this manner. In stage 3, byte sampling, we have a randomized regex style selection of the built-up attribute string, and that lets us pick a selection out of the massive attribute string. There's a fourth stage in here, which is protection, where we hash and encrypt the keyscaler public key. And that's the secret sauce. We've glossed over obviously some of the really low-level technical implementations here, but fundamentally this is how keyscaler devices are able to derive keys. To recap then, devices request authorization and are issued a challenge. They derive a key using the SSS method, and they use that key to sign the challenge and prove that the device is the device it claims to be. This is how DDKG works, and how we make the device the key.